So today we're going to talk about solving trig equations. And the big difference between solving trig equations and solving other types of equations is that where a normal algebra equation might have one or two solutions, these equations are generally going to have an infinite number of solutions. So we'll start with a simple one, solve for theta. I'm using theta as a variable instead of x just to kind of indicate that we're looking for an angle, but I could just as easily be using x. So for this, sine of theta equals 1/2, there's really no algebra to be done here. You're just going to look at the unit circle and find me an angle that has a sine of 1/2. So you see one right in the first quadrant, it's theta equals pi over 6. So if all I were asking you here is what is the arcsine of 1/2, then pi over 6 would be the answer. But I'm not. I'm asking for all angles that satisfy sine of theta equals 1/2. So you just keep looking around the unit circle. We see another one in quadrant 2, and that's theta equals 5 pi over 6. So that's like the basic solution set. But that's not all. So some other things that satisfy sine of theta equals 1/2 would be, let's say we went all the way around the unit circle and then another pi over 6, we would be at 13 pi over 6. Right? Let's say we went backwards, clockwise to pi over 6. That would be negative 11 pi over 6. If we went clockwise to 5 pi over 6, that would be what? Negative 7 pi over 6. So what I'm doing now is I'm just finding angles that are coterminal to pi over 6 and 5 pi over 6. So what we need is just a simple mathematical shorthand to write pi over 6, 5 pi over 6, or any angle that's coterminal to those two. And really the definition of a coterminal angle is that it's a multiple of 2 pi away in either direction, right? It's either 2 pi away, 4 pi away, 6 pi away, negative 10 pi away, whatever, that's going to be a coterminal angle. So here's how we do it. So we're going to let n be any integer, and we're going to consider 2 pi times n. So when we say 2 pi n, we mean really any even multiple of pi, or 2 pi times any whole number n. So if we say theta equals pi over 6 plus 2 pi n, that means any angle that is coterminal to pi over 6. So pi over 6 plus 6 pi, pi over 6 minus 100 pi, that includes everything. And you don't need to say plus or minus 2 pi n because integers can be negative. So you can say plus or minus, but it's redundant. So, right, this includes negative multiples of 2 pi as well. So, and then we just finish up by saying, okay, or theta equals 5 pi over 6, or any angle coterminal to 5 pi over 6, which we just write plus 2 pi. So that's a perfectly fine answer. The most concise way to write this, to me, and I guess the way I would write it, is I would write a comma-separated list, pi over 6, 5 pi over 6, and then I would just put a 2 plus 2 pi n on the end of it. So that, to me, says, okay, the two solutions within the unit circle are pi over 6 and 5 pi over 6, and then this accounts for just every other possible solution that could exist, of which there are infinity. All right, so we're going to level up a little bit. 4 sine squared theta minus 3 equals 0. Same instructions, find all solutions for theta. So the first thing to do in these cases is, this might look like something you want to factor, but it really isn't. You just want to isolate the function. You want to isolate sine of theta. So get sine of theta by itself. So that's not hard. Two moves. 4 sine squared theta equals 3. Sine squared theta equals 3/4. And then you want to take the square root of both sides of that equation. Remember, sine squared theta really means sine of theta squared. So just think about it as x squared equals 3/4. Sine of theta equals plus or minus the square root of 3/4, which simplifies nicely to plus or minus the square root of 3/2. So do not forget that plus or minus, because when we have an equation that has maybe a sine or a cosine squared in it, we're actually going to have more solutions probably within the unit circle. This one's in fact going to have 4. So once again, once you get it down to just sine of theta equals plus or minus square root of 3 over 2, you're just going to look on the unit circle. So the first angle I see is pi over 3. The next angle I see is 2 pi over 3. And then I also have to account for negative square root of 3 over 2. So going down to the third quadrant, I see 4 pi over 3 qualifies. And I see 5 pi over 3 qualifies. So the simplest way to look at these is just to say, list every single solution you see physically on the unit circle, and then just throw a plus 2 pi n on the end. It's just going to be one more thing that you're just going to lose a point if you forget to write plus 2 pi n. So there you go, 4 solutions in the unit circle, plus all the infinite angles that are coterminal to that, and that's the whole solution set. So this one's a little different. Cosine of theta equals 0.7. So this isn't one of those familiar angles you're going to see on the unit circle. So you're going to obviously use your calculator here. You're just going to do theta equals arc cos of 0.7. And that rounds to actually 0.8. So that's 0.8 radians. And that's a point. So now we have to think a little bit. So visualize a unit circle, or just look at one. Somewhere here in the first quadrant, let's say it's like here, is an angle of 0.8 radians. And that angle, I'm telling you, has a cosine of about 0.7. So there's another angle too, and you kind of just have to picture it. If that angle, so cosine is the x-coordinate, right? If that angle has a cosine of 0.7, then this angle also has a cosine of 0.7. Right? They're going to have, so those 2 points are going to have the same x-coordinate. There's some angle in quadrant 4 that also satisfies this. So the easiest way to think about, to write this angle is, well, if this up here is 0.8, then this down here is just negative 0.8 radians. You could also call it 2 pi minus 0.8, whatever that is. 2 pi is like 6.28, so you could do 6.28 minus 28. I think in the case of cosine, it's easier just to call it negative, right? Because remember, cosine is an even function. So 0.8 qualifies, that means negative 0.8 qualifies too, and then you just slap a plus 2 pi n on there. If this were an equation involving sine, we would actually have to go over this way and say, okay, there's an angle over here, right, over like horizontally over here that's going to have the same sign, so we would have to figure out how to express that. Okay, so so now we got one involving tangent squared. It's got a couple different trig functions. Your first instinct may be to divide everything by sine, or maybe to move this sign to the other side. Don't do that. This is something that's already set equal to 0, so that should already kind of be triggering you in your mind that this is one of those things where I need to factor. Factoring in mathematics is one thing that never goes away, no matter how high you go. So setting things equal to 0 and factoring them is like the most powerful alpha algebra move known to man. So don't divide by sine, factor it out. Exclamation point. So you have a common factor of sine of theta, take it outside. Tangent squared theta minus 1 is what you're left over with. If you divided by sine of theta, you'd lose solutions. It's a lot like, it's exactly like dividing by x. If you divide both sides of your equation by x, you're going to lose solutions. Namely, you're going to lose this solution here, sine of theta equals 0. So now we're using that old principle of zero products, where if a thing times a thing equals 0, then 0 is unique in that we must have that one of those two things is 0. There's no other number like that. That's why this is such a power move. All right, so this part of the equation is pretty much already solved. You can just look at the unit circle, or maybe you know that at any multiple of pi, sine of theta equals 0, so 0 is a solution and pi is a solution. Also 2 pi, 3 pi, but we're going to count for all those. This side we need to work with a little bit still. So just isolate it again. We're kind of back to where we were in the last 2 problems ago. Tangent squared of theta equals 1, which means the tangent of theta equals plus or minus 1. Don't forget the plus or minus, because again, you're just going to lose out on solutions if you do that. So just cruise around the unit circle now and think about what kind of angles have a tangent of either positive or negative 1. And if you think about it, it's all the over 4s, right? So the tangent of pi over 4 is 1. The tangent of 3 pi over 4 is negative 1. Right, so all the diagonals, all the like 45-degree angles are going to have a tangent of either 1 or negative 1. So pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. All right, so we actually got 6 solutions within the unit circle, and there generally isn't a way to know with these types of equations exactly how many solutions it's going to have. It could have 6, it could have 10, it could have none. So it's just kind of a case-by-case thing. So again, to write it concisely, I like to put all the angles in ascending order. There's no real reason for that. I just like it. So I'm going to write it as 0, pi over 4, 3 pi over 4, pi, 5 pi over 4, 7 pi over 4, and then don't forget just to pop a plus 2 pi n on the end of there, and that gives you the infinite family of solutions that this thing has. If you look on the unit circle, there would be maybe a more concise way to write this if you put like pi over 4 plus pi n or something, or instead of 0 pi, you could literally just write pi times n because it's any multiple pi. Let's not get too clever. You can if you want to. I'm going to keep it simple. All right. Oh boy, look at this thing. 2 cosine squared of theta minus 7 cosine of theta plus 3 equals 0. So we got cosine squared in there, we got a regular cosine in there, and we got some other stuff. So what you're all saying to yourself, I'm sure right now, is, hey, this sure looks like a lot like a certain type of equation I've seen before. It looks like a quadratic equation. And in fact, this is what we would call an equation of quadratic type. So we are going to factor it just like we would a quadratic. And we're going to do something that comes up a lot in mathematics, which is called making a substitution or a change of variables. So I'm going to just make up a new variable called u. That's the nice thing about math, right? We can just make stuff up and nobody gets hurt. So we generally use the variable u for substitutions. You can use x or something or t or whatever you want instead. It's just a variable. So if I let u equal cosine of theta and I rewrite this original equation, what I have is an equation that is quadratic. This is just a quadratic equation, right? And it can be factored, or if you had to use a quadratic formula or whatever, just using all the tools we remember from algebra class. So we can't ignore the fact that it is a trig equation, but for now, by making a little substitution, we have it in a form where it can be factored. So that's why we call it an equation of quadratic type. This comes up in a lot of different contexts. So, you've all factored before. Here's my general strategy for factoring. I write this, and then I stare at it until I figure out what the numbers have to be, right? So it has to be 2u and u. It's a plus 3 on the end, but it has to be a minus 7. 3 is prime, so the only factors of 3 are 3 and 1. So all you have to figure out is where the 3 goes and where the 1 goes. And if I pop the 3 here, they both have to be minus, right? So it's kind of just a process of elimination. They both have to be minus, so they can multiply to a positive 3. If I put the minus 3 over there, that gives me minus 6u. And then if I put the 1 here, that gives me minus another u to give me my negative 7. So however you do it, whatever your factoring technique is, mine, again, is just kind of to guess until it's right. Okay, so using the principle of zero products, again, we have either 2u minus 1 is 0 or u minus 3 is 0. And let's see, I think I can skip an algebra step here. I either have u equals 1/2 or u equals 3. All right, so that's not the solution because u is just a variable that you made up. I was asking you to solve for theta, right? So you can't stop here. And the last step in any substitution problem is just to basically put it back the way you found it and get it back in terms of theta. All right, so we have it written back in terms of theta. We have either cosine of theta equals 1/2 or cosine of theta equals 3. So you generally always get these equations to this point where you're just saying, okay, what kind of angles have a cosine of 1/2? Well, I'll tell you what kind of angles. angles like pi over 3, right? And if it's cosine we're talking about, if there's an angle in quadrant 1, there must also be an angle in quadrant 4. And that angle, if you just look at a unit circle, you'll see is 5 pi over 3. So we get two solutions off that. And then we have cosine of theta equals 3. So if this were a real lecture, I would say, are there any angles that have a cosine of 3? And you would all say, hell no. Why? Because it's too big. Cosine can't be bigger than 1. Right? It can't be 2 or 3 or -2 or -3 or anything like that. So that's okay. We just don't get any solutions off this part of the equation, right? So you wouldn't even really like theta. You'd just say, okay, there's no solutions from this part, and that's okay. An equation like this could have no solutions, period. But it does have two. So just because we got to something like this doesn't mean there's something wrong. It just means you didn't get any solutions off of that part of the equation. So that's it. We didn't get anything there. There's only two solutions to this. It's pi over 3, 5 pi over 3, plus 2 pi n. One last one for today. Sine squared of theta equals 2 minus 2 cosine squared of theta. So now we just got anarchy, right? We got sines, we got cosines. So the trick here, we need to write it all in terms of one or the other, and it's not. This isn't something we can really factor. So we're going to use the oldest identity in the book, which is the fundamental identity of trig. You know the one. Sine squared theta plus cosine squared theta equals 1. We have to either rewrite sine squared in terms of cosine squared, or we have to rewrite cosine squared in terms of sine squared. Either way, this would work, right? If it works, it works. So we kind of want to pick which one's simplest. So sine squared theta plus cosine squared equals 1. Another way of saying that is sine squared theta equals 1 minus cosine squared theta. That's the same identity, just rearranged, so it's true no matter what. So I think I'm going to replace the left side of this equation with that. So I'm going to substitute that into the left side of this equation. 1 minus cosine squared theta equals 2 minus 2 cosine squared theta. You could have just as easily taken this cosine squared theta and called it 1 minus sine squared theta and gotten to the same solution. So there's no right way here. I think the way I did it was easier because of this 2. Then you'd have to multiply things by 2 and it'd be fine, but I generally pick the way that's simplest. Okay, so now we have an equation that only involves cosine. Involves cosine squared, but so what? We still want to just isolate it, get it by itself. So I'm going to do a little bit of loose algebra here. I'm going to take this 2 cosine squared theta and add it over here. So it's a minus cosine squared plus 2 cosine squared is a positive cosine squared. And then I'm going to go ahead and take this 1 and subtract it over here. So 2 minus 1 is 1. So we got cosine squared theta equals 1. We square root both sides. The square root of 1 is 1, but we have to consider the plus or minus. So that's what we're down to. We're down to cosine of theta equals plus or minus 1, and then it's back to the unit circle. So if cosine of theta is plus or minus 1, the unit circle gives us, okay, the cosine of 0 is 1, and the cosine of pi is -1, and that's it. And then we throw on our multiples of 2 pi on the end, so plus 2 pi n. All right, so that's it. 2 solutions in the unit circle, and then all the other infinite ones. The more, you could write this a lot more concisely by just saying, right, if we were saying theta or pi, or 2 pi, or 3 pi, or 4 pi, or -3 pi, or -10 pi, or whatever, an easier way to say that is literally just any multiple of pi. And a nice way to say any multiple of pi is just to say pi n, right? That's the same exact thing. We're saying any integer multiple of pi satisfies this equation. So you don't have to write it this way. You can. The general rule I always say is just find every solution in the unit circle and then pop that plus 2 pi n on the end. But oftentimes there is a more concise way to write it. So it's up to you.